All right. Hey, y'all. Welcome to this DP curriculum. Today we're on lesson 22, structure 1.5.4 for DP Chem. We're talking about the relationship between pressure, volume, and temperature and amount of an ideal gas shown via the ideal gas equation, PV equals nRT, and the combined gas law, P1V1 over T1 equals P2V2 over T2. Talk about how we get these laws. And what we will be able to do is solve problems relating to the ideal gas equation. Um, we should keep our units in SI, but I'm kind of change that a little bit, and I'll show you why, as well as we're going to learn about the ideal gas constant, the universal gas constant in this equation R. So with that stated, let's just get a move on to the actual lesson. So when we looked at our gas laws, we looked at the three laws, Boyle's, Charles, and Gay-Lussac. So P1 V1 equals P2 V2. Uh, P1 over T1 equals P2 over T2. And lastly, V1 over T1 equals V2 over T2. Now, something you may notice about these is they all just show that these variables always stay constant. So P1 over T1 is equal to some constant, which is how we can get P2 over T2. Furthermore, they assume that all other variables are constant. So in our first law, we assume temperature and moles are constant. In our second law, we assume volume and moles are constant. And in our third law, we assume pressure and moles are constant. But in a system, more than these will usually change. So we can actually combine these three laws together. Noticing pressure and volume are always on top, we keep it that way. P1, V1, temperatures on the bottom over T2 equals P2 V2 over T2, which is also to say it's equal to a constant K. So this is what we call our combined gas law. And if you need to know one gas law, this might be it, or one of two, because the combined gas law can solve for any other one. If you're not looking at volume, just get rid of it. And then look at that. We are back over here to Charles's law. If you're not looking at pressure, you can get rid of it. And now we're looking at Gay-Lussac's law. If we're not looking at temperature, oh, I want that to go away, we can get rid of it. And now we're looking back at Boyle's law. So it doesn't matter. The combined gas law substitutes all three laws and works for any of them. So with that said, let's try using the combined gas law in an example. You can always pause it as I've written out the instructions of it and try and solve it yourself, but we're going to start with a 2.20 decimeter cubed sample of gas at negative 17 degrees Celsius and 100 kilopascals is cooled to negative 173 degrees Celsius and compressed to 80.0 kilopascals. The question is, what is the new volume? So before we even solve this, what we need to do is identify our P1s, V1s, and T1. So P1, V1, T1, and we'll also identify our P2, V2, and T2. So pressure one is 100 kilopascals. Volume one is 2.20 decimeters cubed. In temperature one, well, we notice that it is negative 17 degrees Celsius. We do have to remedy that because we must be using Kelvin. So negative 17 plus 273 is 256 Kelvin. All right. So P2, V2, and T2. So solving for those, we have our T2, which once again, that is going to be in Celsius and it needs to be in Kelvin. We have our P2 and we're solving for the new volume. So new volume is unknown. So we'll write those down. The volume is 80.0 kilopascals. The volume we don't know. And the temperature is negative 173 plus 273 becomes 100 Kelvin. So We can now use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And we're solving for V2. So I'm going to rearrange this to say V2 is equal to P1 V1 over T1. And then the P on the top will go to the bottom. The T on the bottom will go to the top. So times T2 over P2. So if we plug that in, we get 100 times our initial volume, 2.20, divided by our initial temperature, 256, times our new temperature, 100, divided by our new pressure, 80.0. When we plug all this in, you should get a volume of 1.07 decimeters cubed. So that's how you use the combined gas law. It's pretty self-explanatory. You use it just like your other gas laws. The only difference is now we have 6 variables instead of 4. So with that, let's move on to the ideal gas law. Ideal gas law. So we're going to build this law from the laws that we've used before. So we're going to start off with our combined gas law. PV over T is always equal to a constant. So that's what we kind of wrote over here. PV is equal to a constant. We're also going to look at our one equation with moles. We have our molar volume equation. And our molar volume equation says that the number of moles is equal to the volume over our molar volume value, which is 22.7 decimeters cubed mole inverse, which for reference, this is also a constant. So I'll call this constant 1, constant 2. We can rearrange this so that we are setting volume over moles is equal to 22.7. But actually, instead of writing 22.7, I'm going to say constant 2. Much like we combined our gas laws before, we can now combine these two laws. And so we're going to do that. We're going to write our new law, PV over NT is equal to our constant 1 times our constant 2. This, however, becomes a new constant we're going to refer to as R, which is 8.31 joules Kelvin inverse mole inverse. And this is what's known as the universal gas constant. If we now rearrange one more time to keep everything on one line, PV is equal to nRT. And this is our ideal gas law. As it's our ideal gas law, you can actually get all the other gas laws from it by setting certain values constant. This is also within your data booklet, so you do not need to memorize it, as well as the value for R. This is also in your data booklet. So with that said, all we have to do is practice its usage. So let's do some practice, and we'll do 2 problems that also include molar conversion. So number 1, let's calculate the mass of CO2, carbon dioxide, at 20.0 centimeters cubed and 25 degrees Celsius and 100 kilopascals. So before we really go into this problem, we have to identify a couple things in our ideal gas law. So it's PV equals nRT, and these have very specific units. Pressure must be in the units of pascals. Now we've been using kilopascals. Volume must be in the units of meters cubed, and we've been using decimeters cubed. N is still mole. R is given as joules, Kelvin inverse, mole inverse, and temperature is Kelvin. So really, we kind of have an issue with these two. Now, the SI units, the international system that we use for our units, dictates that it must be pascals and meters cubed. However, if we use kilopascals, that's essentially dividing by 1,000. And if we use decimeters cubed, that's multiplying by 1,000. So we can actually use these units instead, and it'll work just the same. The reason I say that, I'll write just to clarify, 1 kilopascal is equal to 1,000 pascals. However, 1,000 decimeters cubed is equal to 1 meter cubed. So by combining them, we can, as long as we use kilopascals and decimeters cubed, or we use pascals and meters cubed, our units will work out just the same. The amount of factorization and the actual magnitude of these values will work. So with that said, we have to start by making some conversions. So what I'm going to do is first try and find out what we're looking for. We're looking for mass. Now for mass, we need first moles. So what we're going to do is change our equation from PV equals nRT to N equals PV over RT. A really quick and easy way to do this is anything that's on the opposite side will stay level. Anything that's on the same side as the variable you want will go down. And the reason this works out is because I'm just dividing by RT on both sides. So you'll notice I quickly can rearrange to get what we need. Furthermore, let's take our pressure. Our pressure is in the correct units, 100 kilopascals. But like I said, therefore our volume must be in decimeters cubed. So 20 becomes 0.0200 decimeters cubed. So these units will work with each other. Our temperature is at 25 degrees Celsius, so we'll change that to 298 Kelvin. That's just 25 plus 273, the conversion that we use. So that gets us temperature, and then R is our gas constant, 8.31. So with that said, N is equal to 100 times 0.020 divided by 298 times 8.31. If I plug this into my calculator, the amount of moles I will get is 8.08 times 10 to the minus fourth mole CO2. What I can then do is just convert moles into grams using our molar mass. I'll put mole on the bottom so that it cancels, gram on the top. 1 mole is equal to 44.01. You might say, where does that come from? Well, carbon is 12.01 plus 16.00 times 2 for oxygen. And that gives us 44.01. That will leave me in grams. And when I multiply this whole thing together, I find that my mass is 0.0356 grams. Therefore, my answer is the mass is equal to 0.0356 grams of carbon dioxide. All right, that is our first problem. We'll move to a second problem. And once again, we'll have to make sure our units are consistent throughout. So this will be a little different. Calculate molar mass. So now we're looking for the molar mass of a gas if 500.0 centimeters cubed at 20.0 degrees Celsius and 101.325 kilopascals has a mass of 0.666 grams. So once again, because we're looking for some type of mass unit, specifically molar mass, we know that molar mass can be converted via moles. So we're going to, once again, just try and find moles. N equals PV over RT. I'm stealing the same equation from before without having to re-solve for it. I'm going to grab my variables. Pressure is already in kilopascals, so I'm going to write 101.325. Volume, however, is in centimeters cubed, so I'm going to move the decimal 3 over and write 0.5000 decimeters cubed. Temperature, once again, is in Celsius, so that's going to become 293 Kelvin. That's 20 plus 273. And R, once again, is 8.31. So plugging all this into my equation, N is equal to 101.325 times 0.5000, all divided by 293 times 8.31. That gives me an amount of moles of 0.0208 moles. This next part is far easier than you might expect. We know that molar mass has the units of grams per mole inverse, or per mole. In other words, grams per mole. Well, I have a mole value and I have a gram value. And so by just analyzing the units in what we call dimensional analysis, I know that my molar mass is just equal to my gram value over my mole value, which is equal to 0.666 divided by 0.0208 grams over moles. And I get a molar mass equal to 32.01 grams mole inverse. All right, so that is the use of the ideal gas law along with some molar conversions. So hopefully this helps and have a great day.